Welcome to Talks. It's our weekly Keystone Talk, and we have it every week that school is in session. Maybe the next couple of weeks we won't have school in session, but in any case, they are talks from luminaries from throughout the technical community. Sometimes we even have business talks, but we've had the inventor of the microprocessor and lots of other people give talks, over 100 of them. They're on the web, on CMU, Silicon Valley, and just search for TOCS. Basically they go till 2:20, and then we have sodas and cookies out in the hall. Please move from this room out into the hall because this room is awfully impacted, and we'd like people to get to know the speaker. Also, when you want to speak, the very front of that black thingy in front of you, you want to push, and you'll see a light up on top of it. Pay attention to the person up here with that light, but stay with your finger on it, and then the camera will record, and the people out in TV land will be able to hear your question. People in TV land, please just send me a chat if you want a question answered. And so today we have Mike Micire, and he's very exciting. Spent his last several years thinking really hard about using robots in disaster and other situations, and he's been involved with many. He's been at Katrina, he's been at the World Trade Center, lots of places where he's gotten hands-on experience that almost no one's ever gotten of trying to use these robots in these real situations. And today he's going to tell us a lot about it, and I think we're very honored to have you here.
Cool, thank you very much. So first of all, thanks for letting me come and talk. Hopefully this will be interesting and educational in terms of some of the experiences that I'll argue that I've been blessed to kind of experience. The talk is going to be one part technical talk, one part business, small business, startup talk, and then the other third is just good humanitarian work. And I've been fortunate enough to find a domain where I can kind of strap all three of those things all into one big lifestyle, I guess you could say. I'm a big fan of kind of reinvention in terms of what I do. So about every five to 10 years, I try to mix it up and switch what I'm doing. The talk that I'm actually going to give you today in that theme would be 2 lives ago. And that this is back when I was finishing my undergraduate and doing my master's work at University of South Florida. Since leaving South Florida, University of South Florida, started a small company that we ran for about 4.5 years. And this is basically a little bit of background and then the story of that small company and the impact that we tried to make on USAR robotics. USAR stands for Urban Search and Rescue. For those who are not familiar, basically those are the guys that after an earthquake or a hurricane or some major disaster go in and basically look for survivors. These are highly trained individuals that are informed as to how to safely enter buildings that are structurally compromised. Certainly structures that you would not want Joe Public running into and possibly injuring themselves. There's all kinds of data where we can show where there's disasters where as many people got hurt after the disaster as they did during the disaster. And so these teams go in and try to mitigate that and actually look for people. So diving into this, one of the tools that as a roboticist, I first came at this from a roboticist standpoint. It was, well, we have these little robots that we can put wheels and tracks and cameras and other sensors on, and can we bring them to bear for this domain? So we're going to dive through that. So the talk, basically, I'm going to break it up into a couple different sections. First, I'm going to talk about the original VGTV and kind of its background. The VGTV is the name of the robot, which I actually brought with me today. This was designed by a company up in Canada, and I'll dive into its past, but it was probably one of the most unlikely candidates as a search and rescue robot. And it was through a couple of good connections that we ended up with it in our arsenal, and it became kind of the backbone of a lot of the research that we ended up doing. And I'll be able to, I'll toss this around. Everybody can get good eyes on it when we start talking about it. And then I'm going to dive into a response that we did at the World Trade Center. So through the work we were doing at University of South Florida, we were requested immediately after 9/11 to go up and assist, because they figured out very quickly that there were lots of very small places that they needed to put cameras, and frankly the equipment wasn't there. So, and then I'll talk about how that led to then the development of what we call the VGTV Extreme. That's the robot basically that my company helped design, and we later built in conjunction with another company. I'll talk about a NASA NEMO project, which is a very fun application of that robot on a completely non-disaster related experience. Some hurricane responses that I was able to do. In particular, we'll talk about Hurricane Katrina and how robots were able to help during that disaster. And then I'll kind of bring it to current time, and you'll kind of see basically the timeline over what I'm talking here is over about 15 years. So this is actually a decent amount of time that we've been trying to inject this technology into search and rescue. So let's talk about the original VGTV. It was designed by Inuktun Services. This is a wonderfully tiny little company up in Nanaimo, Canada. They're on the Vancouver Islands. And they had originally built, you can see this is a nice VHS tape transfer of one of the original designs. This is probably about a second or third generation version here. The big things that it does is it has a camera up front. It has 2 halogen lights to provide lighting. And then of course it has these tracks. And one of its superpowers, which hopefully you can kind of see in the video, is it has the ability to change shape. So it can lie flat like this, and then what happens is it's able to pull this wheel up and it moves into a triangle shape. And I apologize, this guy's a little bit of a stunt double. He's not working today. The working version of this little guy is with some school children today. So hopefully I'll be able to come back and give you a real demo of this little guy sometime. The important part, that shape changing ability allows it to do a couple of interesting things. First of all, whenever, as an engineer, when you sit down and engineer a robot, there's just one rule that you'll learn very quickly, and that's that the environment is not going to change for your robot. Your robot better be able to change to the environment. Okay, so if for instance, I need to get in small places, then the idea that I have a very low form factor and I'm very compact becomes very useful. But if I need to climb over things, you can see that this robot does not have a lot of ground clearance. Okay, that's pretty problematic. The other thing is, as low as it is, if this robot were to drive up to a 2x4 or something, it's basically occluded. Its ability to raise itself up and look over that object then becomes very important to the task that you're trying to do. And so, so that was one of the things why in '96 there was a DARPA program called the Tactical Mobile Robots Program. It was run by a gentleman, at the time he was a lieutenant colonel in the Army, and his name was John Blitch. And he was able to kind of select this robot as a candidate for doing autonomous docking and a bunch of other tasks that DARPA was looking at tackling. And at the time, University of South Florida was on this, we called it TMR, the Tactical Mobile Robots Program. We were on the TMR contract. And so we ended up with a couple of these robots basically in our lab, and we started playing with them. Myself and one of the other students were kind of interested in search and rescue. And it was through that we basically got permission from our program manager. He basically said, look, you guys take these robots and the rest of the equipment I've given you, and during the day, complete your contractual obligations to DARPA. But after 5 o'clock, go take these things out in the world and get them in front of firefighters and see what kind of feedback you get as far as their use. So we were basically given permission to kind of take this equipment out and have fun with it and find other applications for it. So, and I'm going to let this wander around the room. You guys are more than welcome to pass it around. I promise it won't bite. Yeah, go ahead. That little unit, when I don't know what they go for today because I've kind of been out of the business here for a couple of years, but it was around 10 or 15K, which sounds like, okay, well, you just bought a car. Honestly, for especially search and rescue equipment, even just the search cameras that we use for sticking down in piles and stuff like that, those usually go for about 10 to 12K. So it's on par with other equipment that would be used in search and rescue. And actually, there's a good point right here. So be more than willing to interrupt me. I want this to be kind of very interactive. Any of these points, I guarantee I can go into great depth on if you want me to. So help me tune the talk to you guys. Feel free just to interrupt me and we can dive into whatever you want. So let's talk about at least two main applications where we thought this would be useful. One is for the simple search and inspection. It's like what I was referring to there, where search and rescue personnel right now have cameras on poles. And the idea that this would be an extension of that you're going to have the robot go further down into that hole than you would with a pole. Of course, if the void you're going down into has a turn or a bend in it, that pole is only going to be able to basically go to the first bend and then look around, and that's about it, whereas the robot will be able to continue on. So there's some advantages there. We also, on this robot and almost all of the robots that we had two-way audio. When we first started developing this, we started talking to especially some of the medical personnel, and it occurred to us, it was like, oh my gosh, what would we actually do if we found a person? Like, what do we do? We weren't medically trained in this area. And they said, well, actually, one of the easiest and first things you could do is talk to the person. Ask them, are they injured? Are they bleeding? What are they feeling? If they don't answer, then you've determined whether they're possibly conscious or not. And so two-way audio became kind of a base requirement that we had for these robots. So the other thing, the real simple thing that we could do, because it's got the camera, is you can very quickly do a victim assessment, figure out what's going on with them. You can see here, you've got, the early systems were pretty rudimentary, where you've just got a camcorder that we're using, and then this is the cable, which of course isn't a mess, because it almost always is on these cabled robots, and then the OCU. I actually have one of the control units, which we can pass around, and they are really, really simple. This is just, it is actually still labeled a Pelican case, and what they do is they pack all the electronics inside, and the fact that it is a Pelican case is partially due to the fact that this has to be reasonably waterproof when it's outdoors. It's not necessarily submergible, but you have to be able to stand out in the rain and actually use these. So I'll let that go around also. So I agree. There are, so as always with electronics, the engineering trade-offs between it needs to be water resistant and it needs to be able to air cool. You have to be able to circulate air. And so at least in that case, that particular OCU has a decent power supply in it, so it has to be air cooled. We actually had versions of that that were completely sealed. And that we did get rather wet and dirty. They also, and this is just a final video to drive a point home here, they have to be reasonably tough. It's a little hard to see, but you can see one of the robots here that's stuck. And one of the nice things about having a tether is the fact that when that little guy gets stuck, you can lock your boots into the ground and give it a yank back and actually pull it back. I'll go ahead and there's usually a question that comes up right about now, which I'll head off at the pass here, and that's that do all of the robots have to have tethers? And the short answer is no, they don't. But as with any good engineering trade space, there's both benefits and disadvantages to having a tether. The benefits are that you get crystal clear audio and video, regardless of how far the robot is, okay, for the length of the tether. We had some tethers on these that would go up to 300 feet worth of tether. That's really, really important when you finally get downrange and do find a victim and you want to talk to them, that you're not having interference with the video. And you also then have the advantage of having a cord that you can pull back on when it gets stuck. Now the flip side of that is, all right, well, why don't you go wireless? We'll have big enough antennas and big enough power, and let's assume a perfectly spherical cow with respect to being able to have the ideal radio configuration. A couple things end up happening. First, usually that robot is kind of expensive for the operations you're doing, and so chances are you're going to want to put a tagline on it. And as soon as you put a tagline on it, well, you might as well be able to communicate through that tagline, and suddenly we're back to a cable. The other thing that we found is that getting a wireless solution, frankly, that can transmit through steel reinforced concrete and steel buildings and other things is almost impossible. It is a very, very hard problem. Probably one of the hardest RF problems you can come up with in terms of multipath and dB loss and everything else. It's pretty much a nightmare because you've created depending on the building construction, you've created a grounded Faraday cage that you're trying to run this robot around in. And we'll talk about actually a robot that we lost up in New York, up at the Trade Center, which went down, lost its its radio comms, and frankly, we never recovered it. So there's some trade-offs there. Now, the advantage to a tether is it never gets hung up. Your robot, assuming you don't have a tagline on it, is free to wander around the world, however it wants. So there's no one solution for the job. There's kind of trade-offs on either way. So applications. I'm going to give you two quick ones here. One is victim monitoring. It's kind of the situation where you do roll up on someone, and then what do you do? The easiest thing you can do, paramedics, when they roll up on a scene, usually do their ABCs. It's airway, breathing, and circulation. Okay? We can cover breathing and airway just by watching the chest rise and fall. So right there, you're basically through step 2, at least in determining if the person's breathing or not. Okay? So victim monitoring is a good one. I already mentioned being able to at least talk to the person. The other thing we can do is atmospheric monitoring. In this picture right here, you can see this is it's a gas sensor basically that'll go in and tell you whether the environment is hazardous or not. One of the great uses for these robots is to send it in ahead of our rescuers. A lot of this game is just risk management, and it's how much of this stuff do I need to put on before I go down in that void. In a lot of cases, if it's depending on the void, you may have to go in and do monitoring before you ever consider putting a person down in that hole. And putting on one of these suits, if you've never had the pleasure of working in one of these things, it is a real pain. It will take you 30 to 45 minutes just to get set up. And then depending on the air system you've got in there, on a good day, if you've done it a lot, you're probably only good for 45, maybe 60 minutes. If you can baby breathe and not do what they call as far as sucking the bottle down. The other problem is, depending on where you are in terms of the environment, these suits get very, very hot. I did some wonderful training with the Marine Corps where we were out in 100-degree weather, almost literally filling the boots of these suits with sweat. And so it will exhaust you very, very quickly. If you ever have the opportunity to do it, I would say take it because it will humble you very, very quickly as to what our firefighters do. Yeah. So for mine rescue, these particular robots, they could be used. When you get into mine rescue, all of the problems with respect to explosive environments and the safety constraints become hyper sensitive. And the liability actually gets crazy magnified compared to the scenarios I'm going to describe to you here. So the short answer is yes, and there are people that have worked on mine rescue. The two problems you have, and let me step over onto the business side, is that there's not a gigantic market for it. So it's hard to make a business case for doing mine rescue because you're not going to sell a lot of units. And so that's the one side of it. The other thing is in terms of liability and frankly machining, if you took that robot, for instance, and tried to make it able to be used in mine rescue, it would probably double or triple in size just due to seal surfaces and other things that you would have to compensate for. So, but good question. Yeah, go ahead.
Yeah, as long as you're pulling one tube, I mean, do you ever end up pulling 4 tubes and you pass oxygen or water or other things down the tube that gets to what's stuck in it?
Absolutely. So with these original ones, we didn't do that, but you'll actually see when I'm going to ramp up on the evolution of this little guy, you'll see where that almost immediately became one of the useful things that we could do. Can the robot take the victim a radio or a bottle of some bottled water or something like that? That almost immediately became useful. And there's a bit of a footnote there in the fact that so as roboticists, we always come to the game and say, well, the robot is the end. This is the thing that's going to enable it. And what you figure out, hopefully over time, is that really the robot is just there to carry whatever it was that was going to have to go downrange anyway, but do it in a more safe manner. So in a way, it's a bit anticlimactic to the roboticist that thinks that the robot is actually the reason why it's there, but the robot isn't. The robot is just the conveyor of water or radios or medical supplies or information in the case of putting these atmospheric sensors and stuff on them. So long story short, we were working for TMR, and then John Blitch, the gentleman I mentioned before, he had let's just say, a standing agreement with Ray Downey, who is the Chief of Special Operations for the Fire Department of New York. And while the towers were still standing and the planes had already gone into it, long story short, John got a call and said, hey, this is looking really bad. Get your equipment up here. I'm asking for your help. And so John basically called, there was a group of us. There was University of South Florida, iRobot Corporation, Foster Miller, and a lot of different companies and groups that were involved in this DARPA contract. And he basically says, hey, everybody get your equipment in trucks and drive to New York. You know, we've got work to do. And because myself and one other graduate student at the time had been working with our local fire department, which at that point was Hillsborough County Fire Rescue, we at least had a couple people on our team that were actually beginning to be trained up as firefighters. So we were not only bringing equipment to the game, but we actually had some connections into that world. Yeah, and I've kind of already covered that. So this was the equipment that ended up being the most useful. You can see I've already introduced you to the VGTV. This was a kind of a prototype robot that doesn't change shape, but its tracks down here are very, very, very strong. And it's very heavy, which strangely enough ended up being a wonderful asset when it was trying to climb over paper and other kind of light office debris that it was having to get through. So whereas this guy was able to change shape, you can think of this guy as a little monster truck, basically, that was able to crawl over a lot of things. This is a Foster Miller Solem, which is, I think you can kind of argue it's the predecessor to the Talon, which is one of the most popular and successful explosive ordnance robots that's in use overseas right now. So Foster Miller not only had equipment, but they also had personnel that worked, and basically those guys, Foster Miller was actively kind of reworking these robots and sending equipment down on a regular basis. They were based out of Waltham, Massachusetts, and so it wasn't too horrible of a drive for them to go back to the shop, rebuild a piece of equipment and bring it down, and they did that pretty regularly. As you'll see, we broke a lot of stuff. So I'd ask you to look at this video, and this is basically the environment that we were working in. And this is where, for us, and I was actually, we were standing on this ledge looking over and frankly trying to figure out what the heck it was we were going to go do to help in this situation. Luckily, there were people smarter than us that had already figured out what it was we were going to go do. You can see these metal beams. So these are steel beams, and they're hollow on the inside. And when the towers came down, you can kind of imagine that as all of this debris is impacting and driving itself into a big pile, that they're almost like soda straws, are then falling down and spearing down into the rubble pile. We were fairly sure that, and there had been searching going on for quite some time on the surface areas, that there weren't a whole lot of victims to be found at the surface area. That if we were going to find anyone, it was going to be down in the parking garage levels. There were 7 parking garage levels that were down below this structure. And the hope was that one of these steel tubes would have made it into a layer lower than we had been able to find through any of the side access. And so basically that became our job. And for about 11 days, that's what we were working. Was we would go in after the different FEMA teams and the different fire department teams, and they would basically point out a tube that we would need to go inspect, and then we would run the robot down into it. And I think you can see where that little guy, so that little robot with a tether on it is almost uniquely designed. I mean, you couldn't ask for a more perfect design for that. The other thing we ended up doing, and this is a little bit after the initial response, you can see here we've got engineers, and there was a lot of, they're inspecting the slurry wall here, where they would have places where it wasn't safe for them to go look, like is the slurry wall leaking? And so what they would do is the engineers would come up with a plan, they would have the robot basically inserted, or they would tell us, okay, you need to go in from this side. We call this our tether wrangler. So he's the guy who's basically got eyes on the robot from a safe distance. And of course, we ran a tether to him. This is the nice pickle bucket and DV recording unit, operator control unit. And then they would run the robot down, videotape the whole thing. They would pull the robot back up. And then what they would do is, you can see here, you've got fire, you've got an engineer, And then you've got the robot operator translating what it is they're looking at. So he's basically telling them, well, the robot is here, and you've got the wall here, and so this is what you're looking at based on, you know, what you told me to do. It's interesting that you end up having to have a robot translator there. But it's a little weird when you're looking through the robot's eye to figure out what you're looking at. You know, you can even look at the mechanical drawing and say, well, I know it's here, but not everybody has the ability to kind of move the world around in 3 space in their head and describe what it is. So that ended up being one of the big values that we were able to bring. This is what it looked like traveling down one of these tubes. You can see everything's dust covered, of course. All the concrete and glass and fiberglass and everything else as it blew out ended up coating everything. And this was the case almost all of the time, is you would get to the bottom of the void and you would end up with it just packed with debris. Much like in the analogy we ended up making was it's a lot like taking a soda straw and sticking it in a milkshake and then pulling the soda straw out. You're going to end up with a straw that's got the bottom packed with milkshake. In this case, it's just a lot of debris and powder and rocks and other things that end up getting trapped on the bottom.
Why is that?
So it's blurred out because there are actually remains that are kind of behind that pixelization. That is one of the things that we were able to find. So we didn't find any live survivors, but there was a lot of remains that we were able to basically identify. And then the important part there was to flag it so that as they're pulling this stuff out, that they know in terms of doing DNA testing and other things, so they can provide, you know, closure for families and stuff like that.
So how many examples of remains did you find?
That's a good question, and frankly, between the different groups, that actually became kind of highly contested. It's difficult when you're, and I don't mean this to be disrespectful, but it's hard when you're talking about a fractional person to figure out how many people you identified.
Yeah.
But we had, in terms of the different drops that we had, or the different tubes that we went in, and this is just off the top of my head, I want to say it was 3 drops that we ended up finding various remains, and we know within those drops that there were multiple remains within those drops. And that has to do with us being able to identify things like, well, we can see that there are 2 rings or 2 watches in this picture, and it's unlikely that a single person would be wearing 2 watches. So you have to kind of reverse engineer what you might be seeing in terms of remains. And I won't say it's the unfortunate part, but one of the things that we were not able to do from a science and data collection standpoint is we weren't able to be there then when they exuded all of that material and then help them go through and count and get it in a data set.
So there never was any correlation?
Negative. It wasn't. And actually, I can give you a link to it later. So my master's dissertation and one of the other graduate students at the time, basically both of our master's theses ended up documenting all of the, frankly, all of the information that we were able to gather on this. So all of that's available. I can certainly get that to you. Yeah.
How do you go about mapping? You're down there 300 feet away from the operator and through this maze. How do you do that?
The short answer is you're either making it up by scribbling on a piece of paper. When I say make it up, you're making a best guess effort at what it is you're seeing. Or you're just talking it, or you hope you got somebody sitting over your shoulder. Usually when we do our operations, or when we were doing our operations back then, we would have a firefighter or an engineer on our shoulder. Because at the end of the day, we were just kind of like the chauffeur. We would get the robot from point A to point B, and it was really the person that was looking over our shoulder that was really interested in the video that they were seeing. I wish it were better than that. And I can tell you there's groups, actually in particular, the National Institute of Standards and Technology has been, had an ASTM working group that has been working for many years to figure out how to map very highly unstructured environments. That's the tough part, is a lot of the algorithms that we use, your SLAM algorithms and other things, rely on kind of regularity and to be able to do feature matching and other things in the environment. When you go into a completely unstructured environment, then it becomes a little bit tougher to have that be meaningful in terms of the map that you create. And so the short answer is that's still an open area of research.
So you sort of drop breadcrumbs and know where you've been, so you don't repeat your path?
Well, the benefit of having a tether, and you'll see an example of this actually in the case of the Hurricane Katrina. The benefit of having a tether is you basically just pop yourself out, turn 180, look at your tether, and then chase it out. That's actually a trick that we use when we would train firefighters on this equipment. That's what firefighters use. There's actually a whole exercise when they go through training that they'll blindfold you and then hand you a fitting for a fire hose. And you have to be able to feel it and be able to tell them, okay, the male end is this way, so that's into the building, and the female end is this way, so the truck is in this direction. And that's so if you get in a situation where you're completely blocked out, you can just grab your hose and find your way back to the truck. We would basically do the same thing with the tethers. In the case of the wireless robots, you're right. That you're either following your own tracks back, or if you have a tagline on the robot, then you can use the same technique that we're using with the tethers. But that is tough, and that is another one that's still, as far as I'm concerned, an open research problem. So, yeah.
More adverse environments, corrosive, radiation, heat, and so on. I know there's some are waterproof, but this is not what it's highly aversive to people, inhale, but it's not most aversive environment that can be
Are
tolerated.
you talking about this one, or are you trying to talk about another?
Both this one and other ones that
I'll talk about both, actually. So this little guy, as in the one in particular that we used here, was barely water resistant. It had exposed, hopefully you saw when it went around, you saw it had exposed halogen lights. Put that in a flammable environment, you're going to have a bad day pretty quickly. As far as corrosiveness and stuff go, one of the first things I think would go on that is you've got a plastic or rubber tether, and then you've got rubber tracks, which are going to end up getting, if nothing else, in a corrosive or acidic environment, you're going to end up with those getting real slick on you real quick, and once you've lost traction, you're probably not going forward very fast. And so the short answer is, back in these days, yeah, this robot was designed for HVAC inspection. It wasn't designed for those kind of environments. Now, Inuktun Services, which was the group that we were working with, they do a lot of work, still do a lot of work with DOE and kind of the Canadian equivalent of DOE. And so you can kind of engineer the robot to be able to work in those kinds of environments. It just ends up being a different set of engineering constraints, and then you have to be able to build the robot to compensate, and all of the engineering trade-offs that go with that. As soon as you start talking high rad environments and stuff like that, then you start talking shielding, and that starts making the robot heavy. As soon as you start putting cameras in those high rad environments, then the cameras just become really, really expensive because you've got to be able to shield those poor CCDs from all the bad stuff that's going to be hitting them. But it's all possible. I mean, those are all things that the DOE does every day. So yeah. Does that answer your question? Cool. Okay. All right. So moving on. Basically, here is as far as the results goes, we were able to assist the people working at the Trade Center. We ended up hooking up with, these are 3 of the FEMA search and rescue teams. That's Indiana, Pennsylvania, and Virginia FEMA teams. And we worked there from the 11th until the 22nd. And like I said, the best we say is we were able to find remains of victims. As far as lessons learned, and this basically became my dissertation. The short is, we broke every single robot that we took up there. And every single breakage pointed to either a robot that wasn't designed for that environment, which, okay, that's fair, or lack of imagination or lack of engineering on our part. And so these are some of the things we walked away with. The first is a deployment system was needed. You saw that picture where that poor guy had that console and then a nest of coiled cable out in front of him. And you ended up having a tether manager then, so you have a 2-person operation then that's occurring. It would be nice if you had a deployment system for the cable so you could turn that into a 1-person operation. Autofocus would be, and zoom capability would be very good. This little guy does not have zoom. It never fails. That you saw where in that one video where he got down to the bottom and the robot stands up and is basically, we're trying to look over that little pile of debris, and there was no zoom capability on the camera, and so wherever you get is kind of as far as you're going to go. The ability to zoom would be really, really useful. Longer tether with strength to withstand tension. You saw in that earlier video where you lock your boots in and pull on that thing. Well, you've got all nice little copper wires that are running through there. Do that more than a few times at a decent strength, and you actually end up breaking the conductors, and then you're out of service.
There's no stainless capability.
we later did Kevlar reinforcement as one of the improvements that we did, and that actually, we got to the point where we were able to hang the robot from its own tether, shock load it, and do all kinds of stuff. So steel actually is a little tough just in terms of bend radius, but you throw Kevlar in there and you're actually able to get a word in edgewise in terms of being able to pull on that thing pretty decently. Adjustable body clearance. So this robot had adjustable profile, but you saw, I mentioned it was very low to the ground. Well, a lot of the time in the videos that we had was spent with the robot just trying to get over things. And so can you get it up off the ground, kind of frankly like what we do with trucks, right? There's a big difference between a sports car and a monster truck, right? And then a lot of that has to do with ground clearance. Multiple types of tracks. So the one track does not fit all. You get in some environments that are dusty, you want a whole lot of traction. But if you get in an environment where it's wet and you might be on carpet, then that's a completely different traction environment. It turns out tracks ended up being the bane of our existence for a very long time. Tracks are deceptively difficult. We also had a robot, one of the robots that went down into the void of the video you saw actually ended up losing one of its tracks. And that was due to a couple different reasons, but the important part was there was nothing kind of within the robot that was designed to keep that track from throwing itself off. And again, once you lose your track, you're done because you're not on wheels at that point. And most importantly, the robot needs to be waterproof. That's not because we need the robot to run underwater. That's because when you run robots through bad, nasty things and you bring it back out, you have to decon that robot. Exactly, because you don't want to be bringing that bad stuff back into your base of operations. And that's kind of rule number one as far as any disaster stuff is concerned, is you have to be able to decontaminate your robot. And so I'll talk about how, basically, this is the lessons learned kind of out of at least my master's dissertation. This became kind of the engineering, or the top level engineering requirements for the improvements then that my company made after I graduated. So let's, oh, go ahead, yeah.
You know, these things that you're saying are they seem so completely reasonable that I'm shocked that they hadn't thought about it. Why weren't people taking those kinds of things seriously before that? They were just too consumed with other things, or they were idiots?
No, well, it's certainly not the latter, because we were one of the groups that was working on it, so I don't like to think that we were idiots. There was a lot of focus on larger robots. So if you guys are familiar with like the PackBot size, and you saw the Solon there, the Talon is a little bit larger than that. Those were in what they call the man-packable class of robots, is the DARPA or the DoD terminology for it. And those were borrowed kind of from the explosive ordnance world. And a lot of focus was on those because, all right, they can run off batteries, we can put a lot of sensors on them, so we can do things like mapping and other kind of interesting things, and your ability to carry sensors becomes a lot easier. The little guys, we were like, wow, why would we want to limit ourselves to these tiny little tethered things, because it's got a tether, you can't put a lot of payloads on it. And so it kind of flipped. The kind of running joke in disaster response is you're always prepared for your last disaster. And so you'll see where in the case of the World Trade Center, we walked away with that as our lessons learned. And that's because that disaster taught us that small robots and very rugged robots are very important. It's not that we didn't think those were important, but they certainly weren't researchy things to go do. Making something rugged is hard to sell to the National Science Foundation as a good, as a good proposal.
People didn't think small was beautiful, is what you just told me.
There wasn't a precedent that said small is where this needs to go. And we were able to show up with several truckloads worth of DoD equipment, probably, and I'm guessing here, but you're talking 500,000 and upwards worth of robot equipment that showed up that never got taken off the truck because it was just too big. And the sensors were too fragile. And a lot of the kind of academic research that had been occurring just wasn't relevant, at least in that instance. It was more, just give me eyes and sound down in that hole, and then we'll go from there. So, yeah.
So the lessons you're just now talking about, aside, whatever, does that relate to the recent Fukushima nuclear situation?
So Fukushima, and you'll see later when I talk about the Katrina, a lot of the stuff that we're hanging our hat on as far as small size here, when you get into, so this was a completely unstructured environment. When you get into a partially structured environment, then the larger robots come back into play, because when you're this small and the world is still large, everything is an obstacle to you. So your ability to go out and now manipulate the environment, if that door is shut, your ability to be large enough to reach up and turn a doorknob or something like that then becomes important. So again, to me, this is just a wonderful engineering exercise, and to see that there's not going to be this like this holy grail of this is the robot that does all things for all tasks you saw. You're actually going to need kind of an arsenal of different robots to take in all the different tasks. So, you had a question?
I want to ask, you maybe have an upcoming slide here, but about tracks and such. There was a shot of a picture of a robot there that had a track that was almost all track on the bottom. How did that function in different environments?
It did well, and actually that robot, you will see that very unceremoniously the robot that becomes developed by my company looks suspiciously like that one in terms of the form factor of the tracks. Tracks, it's a double-edged sword in that robot, yes, it has very wide tracks. The big thing that you're doing there, when you have the tracks that almost cover the entire surface of the robot, it's difficult for it to get things caught up underneath it and to high center is what we call it. And that's where you roll up on something, and then as you get over the top of it, whatever that is, then gets caught on the underbelly of the robot, and its tracks aren't actually hitting the friction surface that it needs to get over it. So the engineering thing is, well, we'll make the whole thing tracks, which sounds like an obvious solution until then the next person comes to you and said, here's my sensor. And now suddenly you have to figure out how to have this sensor passing through tracks that are moving and moving very wildly in terms of as they're going through the terrain. So this is, again, from an engineering trade-off and trade space standpoint, this is a tough nut to crack, because you've got a lot of different compromises you've got to make in terms of the design. So, yeah.
I wonder if you could talk a little bit more about sensors being delicate or bulky, because these days I'm used to seeing all kinds of small sensors for environmental testing to laser rangefinders or interferometers. I mean,
Yep.
It all seems small and light and reasonably sturdy.
Sure. So let me hit a couple of those. So at the time, the sensors that we were using, one would be a laser rangefinder. The main manufacturers that were out there in those days was like SICK and some of the other like planar rangefinders. The problem with those is get them dirty and they're useless. Get a little bit of dust on that viewfinder and you're going to be ranging to wherever the particle is that's sitting in front of your laser. They're also very, very power hungry, and at the time were very heavy. You were talking about laser rangefinders that are about the size of like a small coffee maker.
If you've got a cable connecting you to an outlet that you're plugging along, does power really matter?
Well, we didn't have an outlet on the trade center. That's one of the problems. You're carrying your battery, you're carrying your power source with you, because you probably don't even have a generator if it's in an environment that may be flammable, or you're having to work around people, because generators create carbon monoxide, and that's a bad thing too. So if you're carrying your own power, and then the size and weight of the laser rangefinder ends up approaching, like in the case of a SICK laser, a SICK laser weighs more than the entire robot that we were using to get in some of these voids. So that's one of the problems there. The other real common one back then was using sonars. Sonars end up being extremely problematic as far as being able to get accurate ranging information in highly reflective environments, which reflective for sonars are having glass or metal surfaces and stuff like that. Then the flip side of that is, well, go to IR, just do IR ranging and stuff like that. Well, IR ranging fails miserably as soon as you have sunlight anywhere near it, because the flaming ball in the center of our universe tends to be a pretty decent IR source, and so it ends up flooding out the sensor. So there are now, a decade later, the sensors are better, but even some of the very, very small laser rangefinders that are available today are still susceptible to dirt and materials and mud and other things, which these robots are going to be exposed to almost immediately. So it's kind of tough. You could, and actually I've heard that suggestion many, many times, and I've yet to see anybody do it right. So good suggestion, yeah.
Do you ever take the robot and drag some sort of cable down to the deep location, anchor the cable, and then something else travels along it, so then you can drag sensors down and other devices?
I can actually think of 2 projects off the top of my head that tried to do exactly that, and it is, let's put it this way, I think that would be a good experiment to do and a good implementation. I've just yet to see anything that was an implementation that was robust enough that it kind of stuck and got used. So yeah.
I want to make sure that you get through your slides.
I do too. So timing wise, am I dead at 2:30?
You're dead at 2:30 for sure.
Roger that. Okay. So let's move then. So basically we took what was this design that was literally kind of on the back of a napkin. I actually was lucky enough to have a good artist that was in my company. And so she would take my very, very horrible designs and turn them into these wonderful drawings. The important part here, you can see we're taking the original chassis from that VGTV I showed you. And the important part here, and this is why I would argue draw things out first, is she actually drew this wrong in terms of the way the wheels moved. And that ended up being a great eureka moment for us as far as this, oops, I dropped my mic, as far as this platform goes. And that's that we figured out, well, wait a minute, we can actually dramatically increase the wheel diameter if we interleave these 2 front wheels. And that got us the ground clearance that we needed, basically, to get this thing. I think at the end it ended up being like 1 3/4 inches off the ground. Another idea was we were going to have this be removable, so the actual payload. Whatever robots you build, the customer is going to want a different payload in it. And so the idea is we would make that plug and play. We ended up building, this is one of our first prototypes, and this is actually the chassis that I just handed around to everybody with the larger wheels. The important part here, and this is kind of a note from a small business standpoint, is you can see those wheels are made out of wood. That is literally me spending a week in our shop with a drill press and a bandsaw prototyping these things out of wood. Today, you get a lot of engineers that just get all hung up around, we need to CNC this thing, and let's get it into CAD. And so you end up with these week-long development cycles just to get the prototype. And I would argue, forget that. Just go get some wood and just acid test it quickly so you can fail and fail often and fail quickly so you can get to the solution you need. Now, one would argue, well, Mark, the wood doesn't look real good. So what we did was, and I can't tell you how many VC tables I had this thing sitting on, where we took the wood wheels and we put them in fiberglass and sanded them, took what was paint gun that was normally used for automotive applications, painted them, and they look gorgeous. I actually still have these in a box today, and they're one of the best examples of robot wheels for tracks that I've seen, and they're made out of wood that we picked up at Home Depot. Long story short, we did finally get through the CAD design on this, and this is the little guy, the VGTV Extreme. You can see that it grew a little bit. One of the things was, remember I said it needed to be waterproof? So it's got a lot more metal. That just has to do with the seal surfaces that you have to make the waterproofing happen. We figured out, as a real quick footnote, we knew it needed to be waterproof, and we were like, okay, well, how waterproof does it need to be? Usually they talk about this in terms of depth rating. You know, it needs to be to 1, 2, or 3 atmospheres. So we actually talked to the group that was doing our machining. We said, can you manufacture something that's waterproof to 1 atmosphere, 2 atmospheres, and 3 atmospheres? And that has to do with the machining tolerances and the seal surfaces that they have. And then we took each of those boxes, and I actually went down to the fire training grounds, and we laid the boxes out on the parking lot, and I got one of my friends to bring an engine over, and we fired up the hose and blew these boxes around in the parking lot, and then opened them up and figured out which one broke open. I could have done all kinds of static fluid, modeling and figured out what depth rating we needed to get. But the hint there is dynamic pressure is very, very hard to calculate. Never try to calculate what a firefighter is going to do to your equipment would be the other footnote there. And the bottom line was, just with that one simple test, we were able to figure out that 3 atmospheres is what this little guy needed to be waterproof to. And so that's what kind of bulked him up a little bit.
And these guys are all floatable.
No, actually, they sink like a rock. Yeah, it's just shallow. This is, frankly, although this ended up being one of our promo videos, this is myself and one of the other engineers just goofing off down off of St. Pete. So we'll get into this video in a second. So another little footnote. While we were doing all of this, I am a big fan of saying there's no better way to understand your customer than to become your customer. And so myself and one of the other coworkers we actually put ourselves through fire school. So done with our masters, went down to the local community college and signed up for the fire academy. and we're there. We were the, they used to call me the old man on the fire ground because all these kids are fresh out of high school, and went through fire school and became certified as a firefighter. That was a huge eye-opener for me. In that before this, we had a lot of things that we did, but we did it because we were imitating the firefighters. Suddenly, we understood why we were doing those things, and that provided all kind of insight as to why then the equipment needed to be designed the way we were designing it. This eventually ended up with, so going through fire school, then got on at the time it was the regional search and rescue team, Florida Task Force 3. Later got on a FEMA team, so that was Massachusetts Task Force 1. And actually now I'm on the California Task Force 3 search and rescue team as a technical search specialist. So there's a lot to be said for getting, just don't try to interpret your customer. In some cases, become your customer, and you'll learn a lot that way. So remember I said I was talking about deployment systems. So again, you draw on a napkin, and we went through a couple of iterations. You can see we had a couple different designs that we worked through. This was a prototype that we came up with, which was pretty sexy in terms of a hard shell, and you can see the robot in the back there. At the end of the day, though, we were able to scrub through that pretty quickly, and it turns out that a cloth bag that we were able to get custom sewn, that the important part here is it's compatible with the harnesses that the FEMA teams were already using. So the thing was, we didn't, and this was out of discussions that we had with the rescue guys, was we don't want to have a robot guy. We want to be able to put the robot on people. And so if the person already has a harness on it, then make your equipment compatible with that harness. It ended up being a lot cheaper and a lot less complex than the very sexy engineering solution that we had earlier. The other important part, mentioned batteries. This ended up being our battery solution. And that was, these are lithium ions. That was a solution after I lugged about 10 pounds of lead acid batteries during one of the hurricanes and decided that that was not a fun afternoon. So very quickly, as a side note, we ended up hooking up with NASA for a NEMO operation. I'm going to cut to the chase here. Remember I said that that thing was depth rated to 3 atmospheres? Well, it turns out NASA and University of North Carolina, Wilmington has a habitat that's down in Key Largo that's sitting at about 3 atmospheres. And NASA wanted to see, this was right after Columbia, and they wanted to, the Columbia disaster rather, and they wanted to see how feasible it was to have a robot inspect the outside of a structure. So the analogy was, you know, you're on a moon base or you're sitting in shuttle and you know you have damage to your tiles or your wing edges. How difficult is it for somebody inside to inspect what's going on outside? And so long story short, for about 2 weeks, we ran this little guy around, and he is brand spanking new, like fresh off the CNC machine and fully assembled. And then we took it down and ran it around. It's a nice Mount Everest spec, which is kind of the spec when you look at like the tough books and other hardcore laptops. That, you know, this can survive negative, 50 degrees on the top of Mount Everest. Okay, none of us will probably end up going to Mount Everest, but it's good to know that your laptop can survive that. This was our Mount Everest spec in the brochure. It's like, this thing can survive, 2 weeks sitting at a full 3 atmospheres, down on a coral reef in Key Largo. In this case, so the aluminum was anodized, and so we were able to kind of head it off at the pass a little bit there. Of course, you end up, the big thing with corrosion is you end up with interaction between the steel and aluminum parts on each of your surfaces there. So we frankly had to fresh water clean the robot every time we pulled it out to keep that from happening. Exactly what you would do with a boat, basically. So we ended up with a user interface where they were able to remote control it from Houston. And long story short, it was a success, and it ended up being both a great experience for us and NASA got some good data out of it. So let's go real quickly through this. So then, come Hurricane Katrina, we had worked a whole bunch of, the whole 2004-2005 hurricane season. My team, as a search and rescue team, was very busy, but it turned out that it was Katrina where we got our first opportunity to really use robots. And long story short, the devastation was substantial. You can see that's a person, basically in a debris field, and so this was the kind of environments that we were working in. Not a lot of opportunities to use robots there, but we ended up with cases like this, where this is a partially collapsed apartment that was damaged basically by storm surge. And you can see there where that's not a garage, that's just a car that was pushed through the wall, and then the second floor is collapsing on it. We were able to, we basically, the safety guys, instructional engineer says there's no way you're putting even dogs in this structure. And so we ran the robot from, we did 2 entries on it. We ran it from the front door to the back door, and then from the side door around, and actually looking for people. And so you can kind of see this is, there's actually online, there's a whole, you can see basically the uncut version of this, of all of the running around in the house and kind of looking for people. As far as successes, again, the bottom line here was we were able to do a front to back door search, and that had not been done before. And that was a nice little data point and a bit of a reward for us after all of this effort. So, but the big thing that we walked away with, and I hinted at this a little bit earlier, is that one size doesn't fit all. This is the VGTV, and then this is I was talking about the iRobot PackBot that's behind it here. You can see it's a much larger form factor. Frankly, the PackBot would have been able to do, I think, just as well as the VGTV did in that partially collapsed structure. So we kind of walked back from this and said, well, you know, maybe small isn't the answer. Maybe we need, you know, a bunch of different robots. We mentioned in mine safety, intrinsic safety. One of the things we had in Biloxi was when all those houses moved, they used LP that was piped into the houses. You take a house and shift it on its foundation, and all those gas lines break. Suddenly you have houses that are filled with gas. We were fortunate that our hazmat guys could run ahead of us and kind of tell us whether we were in an environment where this little guy could provide a hazard for us while trying to keep us safer. So I won't dive into all those because each of those is, I can dive into those. We talked about payloads. This is a good example. We started looking at how can you put different things on it in terms of being able to carry it in. And then where are they now? So we actually built quite a few of these things. This is a state team, so New Jersey Task Force 1 actually has one of these in their cache. University of Massachusetts Lowell, where I did my Ph.D., they have one of the green one that you were seeing there. The Center for Robot Assisted Search and Rescue, who's now at Texas A&M, has 5 of them, I think. And SPAWAR down in San Diego uses them for a couple different things. So, very quickly, the conclusion is, and this is after, call it a decade worth of development, we still don't have a perfect robot, and this field is still growing and learning. As you can probably, if any of you have followed the DARPA solicitations, DARPA even just put out a grand challenge related to this. I think it's, especially after Fukushima, this is just as relevant now as it was 10 or 15 years ago. The sad part, the unhappy ending for my company, if you're curious, was just the fact that it's a very, very small market. And unfortunately, there was a group that came in and decided that we needed, we talked about intrinsic safety, that they wanted safety standards related to this robot, or related to robots used for search and rescue, and that FEMA and DHS shouldn't purchase robots until those safety standards are put in place. That took a tiny market and destroyed it overnight. And so basically I had to then go to my board and say, I'm sorry, we don't have a market, and we ended up closing our doors. So hopefully there's still a need for it, and when the market does emerge, we've got a lot of really, really good equipment that could come to bear on this problem and hopefully provide some value for groups that are out there. So, all right. Thank you very much.
It's a really exciting, fascinating story. Sorry about the sad ending. In general, I'd
be Captain Buzzkill.
I'd rather spend another 15 minutes here asking questions, but I think we'll just move it out into the hallway. Sure. And I'm sure a lot of people here are very excited to be talking to you, and I'm very proud that we got you to come. So
awesome. Thank you very much. Absolutely, and it'll humble you pretty quickly.